August 15, 1940, Kent, England, 11:30 in the morning. 22 Spitfires claw for altitude over the English Channel. Below them, more than 80 German bombers and fighters cross the coast in tight formation. Radar plotted them 40 minutes ago. Every second since has been a race the RAF is not built to win. Here's the number that should terrify every pilot strapped into a Spitfire cockpit this morning. Their engines are burning 87-octane fuel. German pilots know it. British engineers know it. And 87-octane fuel means less boost, slower climb, and a hard ceiling on how long a Merlin engine can run at full throttle before it tears itself apart. Fighter Command has done the math. At current performance, RAF squadrons can meet the Luftwaffe over the coast, but chasing them inland, fighting at altitude, stretching a patrol to catch a formation forming up over France? That math doesn't work. Not on this fuel. What the pilots climbing into their cockpits this week don't know is that the equation has already changed. Weeks earlier, tankers had begun quietly unloading a different fuel at British ports of fuel with 13 more octane points, refined by a process that the world's largest oil companies had spent a decade calling impossible. The man who built that process wasn't a petroleum chemist. He didn't work for an oil company. He held no advanced degree in the science that would define the Battle of Britain. He was a French mechanical engineer who'd once used a Bugatti race car to test gasoline made from crushed clay, and for 13 years, nearly everyone who mattered in the oil industry told him he was wasting his life. This is the story of how a useless experiment became the fuel that let Spitfires fight longer, climb faster, and reach deeper into enemy skies than the men who built them ever thought possible. To understand why this mattered, you have to understand what a fighter engine actually needs. An engine's power depends on how much you can compress fuel and air before it ignites. Compress too much with low-grade fuel, and it detonates early a violent knock that can crack pistons and destroy an engine mid-flight. Octane rating measures resistance to that knock. Higher octane means an engine can run higher boost pressure safely, which means more horsepower, faster climb, and higher ceiling. In 1940, this single number would decide who owned the sky over southern England. The problem was production. In the early 20th century, refineries made gasoline through thermal cracking, using extreme heat and pressure to break heavy crude oil molecules into lighter ones. It worked, but it was crude. It converted only a quarter of a barrel of crude into usable gasoline, and the octane ceiling on that gasoline sat stubbornly around 70 to 72. Engineers had known since the 1910s that a catalyst, a substance that speeds up a chemical reaction without being consumed by it, could theoretically crack oil more efficiently and at a higher quality. Gulf Oil tried it with an aluminum chloride catalyst in the 1920s. It failed. The catalyst degraded fast, coked up, and cost more than it saved. By the early 1930s, the expert consensus inside the American oil industry had calcified into something close to doctrine. Catalytic cracking of petroleum was not commercially viable. Thermal cracking was the ceiling. Anyone chasing a better process was chasing a fantasy. That consensus mattered enormously to the men who'd soon be flying fighters. Britain had no domestic solution. Standard 87-octane aviation fuel, produced through conventional refining, was what the Merlin engine was designed around and what the Air Ministry believed it would have to fight the war on. Test pilots and engineers at Rolls-Royce suspected the Merlin could take more boost, more compression, more punishment if only the fuel could handle it. But without a scalable way to produce higher octane gasoline in bulk, that extra performance was theoretical. A locked door with no key. The stakes were not abstract. Every mile per hour of climb rate Every extra minute of full-throttle endurance was the difference between a squadron reaching altitude before the bombers arrived or getting caught climbing into a fight they couldn't win. Fighter Command's entire strategy scramble, climb, intercept depended on performance margins that, on paper, Britain did not yet have. The key that would unlock that door had already been forged. It just hadn't been recognized yet because the man who forged it had spent over a decade being told by people with far more credentials than he had that it couldn't be done. Eugene Houdry was not supposed to be the man who solved this. Born in 1892 outside Paris, Houdry trained not as a chemist, but as a mechanical engineer, graduating first in his class from the École des Hautes Études in 1911. He joined his father's steel business. He served as a lieutenant in a French tank corps during the First World War and was seriously wounded at the Battle of Juvincourt in 1917, earning the Croix de Guerre for his conduct under fire. His real credential, if he had one, was speed. Houdry raced Bugattis. He was obsessed with engines, fuel, and performance, an enthusiast's obsession, not an academic's. In 1922, a fellow racing driver showed him something strange, a bottle of gasoline distilled from lignite, a low-grade brown coal, by a pharmacist in Nice. France had almost no domestic oil, but plenty of lignite, and the country was gripped by fuel shortage anxiety after the war. Houdry, then 30 years old, with no chemistry training, looked at that bottle and made a decision that would consume the next 2 decades of his life. He quit his father's steel company and began chasing a fuel process that professional chemists across Europe had already dismissed as impractical. He spent years experimenting with catalysts that could crack heavy hydrocarbons into lighter, higher-octane fuel without collapsing under their own byproducts. Most catalysts tried before him failed the same way they worked for a few hours. Then a layer of carbon coke choked them dead. Houdry's insight wasn't a single flash of genius. It was patience. He found that an ordinary porous clay, a material called Fuller's earth, the same stuff used to filter cooking oil, could be burned clean and reused, cycle after cycle, without losing its catalytic power. It was, on its face, an absurd claim. A former steel business engineer with a racing hobby claiming that crushed clay could outproduce the largest oil companies in the world. By 1929, backed briefly by the French government, Houdry built a demonstration plant to turn lignite into gasoline. It worked, but it was too expensive to matter, and Paris pulled its funding. Most men would have stopped there. Houdry didn't. He'd learned something the failure couldn't take away from him. The same clay catalyst that cracked lignite tar could crack crude petroleum too. He just needed someone willing to let him prove it at scale. Houdry moved to the United States in 1930, backed by Vacuum Oil at a small research plant in Paulsboro, New Jersey. It was here, hunched over lab-scale reactors barely larger than oil drums, that he ran his crude oil experiments, testing his clay catalyst not on gasoline theory, but on actual crude, cycle after cycle, refining the regeneration process that let the catalyst be burned clean and reused indefinitely. The results on paper should have been front-page news. Where thermal cracking yielded gasoline around 60 to 72 octane, Houdry's catalytic process was producing fuel in the 80s, a jump that at industrial scale would change what every combustion engine in the world was capable of. Instead, the reaction from the industry's experts was closer to dismissal. Established oil men had watched Gulf's aluminum chloride catalyst fail a decade earlier and treated Houdry's clay process as a variation on the same dead-end, technically interesting, commercially worthless. Interesting laboratory curiosity was the kindest verdict. The harsher ones simply called it impossible to scale, that no catalyst could survive industrial throughput. that Howdry was chasing the same mirage that had already burned other engineers. Then came 1933. The Great Depression gutted demand for oil. Vacuum oil merged into Saucony, and in the shuffle, Howdry's project was effectively orphaned, a promising process nobody wanted to pay for. He kept it alive on his own money. He came from a wealthy family, and he spent it, refusing to let a decade of work die in a filing cabinet because the timing was bad and the industry's consensus was against him. It was a quiet, grinding kind of workshop drama, no dramatic explosion, no single eureka moment caught on film. Just a man running the same reaction over and over, refining the regeneration cycle, proving the numbers held up not once but consistently, batch after batch, while the men who could fund it at scale kept saying no. The turning point came through persistence rather than persuasion. Clarence Thayer, an engineer at Sun Oil Company, worked closely enough with Howdry to see what the bigger companies had missed, and compared his stubbornness to that of a bulldog. In 1933, Howdry secured a meeting with Sun Oil's president, J. Howard Pugh, and his vice president for refining, Arthur Pugh Jr. Where the giants of the industry had shrugged, Sun Oil, a mid-sized company hungry for an edge, agreed to back him. Sun Oil and Saucony Vacuum signed a joint development agreement to push the process from lab bench toward something that could run around the clock. Howdry finally had a workshop big enough to prove he wasn't chasing a mirage. Even with Sun Oil's backing, Howdry still had to win over an entire industry that had already made up its mind. The proving ground was Marcus Hook, Pennsylvania, on the banks of the Delaware River. On March 31, 1937, engineers charged Howdry's first full-scale commercial unit, designated 11-4, with 15,000 barrels of the thick, sludgy residuum left over after Sun's conventional thermal crackers had already squeezed out every drop of gasoline they could. It was, by the old standards, waste oil, garbage, useless. The heat climbed to 900 degrees. Pressure built. And as engineers watched the gauges in tense silence, the vaporized residuum passed through Howdry's macaroni-shaped clay catalyst pellets. When the run finished, the yield sheets told the story. 7,200 barrels of gasoline extracted from oil the industry had already declared spent at an octane rating of 81. Compared to the 60 that conventional processing squeezed from the same crude, that number should have ended the argument. It didn't, not immediately. Skeptics inside the oil establishment questioned whether the process could be sustained at true industrial throughput, whether the economics would hold once the catalyst had to be regenerated thousands of times over. Howdry had built a machine that worked. He still needed the industry to believe it. The confrontation came in November 1938 in the ballroom of the Stevens Hotel in Chicago at the American Petroleum Institute's annual meeting, the industry's most important stage. Arthur Pugh Jr. stood up to deliver a paper with a deliberately unremarkable title, Catalytic Processing of Petroleum Hydrocarbons by the Howdry Process. He laid out the yields, the octane numbers, the economics. For a long moment, the room sat in stunned silence, absorbing what they'd just heard, years of dismissal colliding with irrefutable data. Then the questions came, fast and skeptical, before the room finally erupted into applause. The engineers and executives who had spent a decade calling catalytic cracking a dead end were now watching it work in front of them, backed by numbers no one in that room could argue with. Sun Oil's president, J. Howard Pugh, gave the final approval to push Howdry units into full production. It wasn't a single dramatic override of a bureaucracy, it was years of accumulated proof, finally breaking through institutional inertia at exactly the moment the world needed it most. By 1940, 14 Howdry catalytic cracking plants were running across the United States. Their output became the base stock for 100-octane aviation gasoline fuel with 13 more octane points than the RAF's standard supply, shipped across the Atlantic just as the Battle of Britain began. The fuel reached fighter command squadrons in the summer of 1940. Ground crews switched supply lines. Pilots noticed the difference before the engineers finished writing the reports. The numbers, once tested in combat conditions, were stark. On 100-octane fuel, a Spitfire's Merlin engine could run at 12 pounds of boost instead of 6, nearly doubling the safe power ceiling. Top speed increased by roughly 25 miles per hour at sea level and 34 miles per hour at 10,000 feet, the altitude band where most Battle of Britain dogfights actually happened. Climb rate improved sharply, and critically, the higher octane fuel let pilots run more efficient cruise settings without sacrificing the combat boost they needed at the moment of contact, stretching patrol endurance and extending the radius at which squadrons could safely intercept, chase, and return, deepening fighter command's reach by dozens of miles into contested airspace over the Channel and the French coast. Picture a Spitfire squadron scrambling from Biggin Hill on a September afternoon, 1940, months earlier. That climb to 20,000 feet would have taken longer, burned more fuel doing it, and left less margin to chase a formation further out before turning for home. Now the same aircraft claws upward faster, arrives with fuel and altitude to spare, and can push further out over the water before the gauge forces a decision. German pilots felt the shift before British intelligence confirmed it. Luftwaffe combat reports through the late summer of 1940 increasingly describe RAF fighters climbing faster and engaging at altitudes and ranges German pilots had assumed were safely beyond reach, a performance jump nobody on the German side could explain from airframe changes alone, because there weren't any. The Spitfire hadn't changed. Its fuel had. Germany's own aviation fuel, refined largely through conventional and synthetic processes, never cleanly cleared the 90-octane mark during this period. The performance gap that opened over the skies of southern England in the late summer of 1940 wasn't just pilot skill or radar coordination, though both mattered enormously. It was, in no small part, 13 octane points that one industry had spent a decade insisting were commercially impossible to produce. Fighter Command's official tallies from the Battle of Britain credit the RAF with a favorable exchange ratio through the height of the fighting British losses running lower than the Luftwaffe's for extended stretches of the campaign, a margin that squadron commanders and post-war analysts alike partly attributed to the extra performance headroom 100-octane fuel provided at exactly the moments that mattered: the climb, the intercept, the extended chase. One RAF veteran, reflecting decades later on what that extra margin meant, put it simply: those few extra miles per hour, that faster climb, were the difference between catching a bomber formation and watching it disappear toward London. Because of that fuel, he said, a lot of us came home who might not have. Howdry's 14 plants and the dozens more built on his licensed process through the war kept producing. By 1942, they were supplying the overwhelming majority of America's catalytically cracked aviation gasoline fuel that powered not just Spitfires and Hurricanes, but the Mustangs, Thunderbolts, and heavy bombers that followed them into the skies over occupied Europe. Eugene Howdry never flew a combat mission. He never stood on an airfield watching a squadron scramble. He spent the war largely in labs and refineries in Pennsylvania and New Jersey, tuning a process that most of the industry had told him, for over a decade, would never work. He didn't stop innovating once the war ended. After 1945, worried about what automobile exhaust was doing to city air, he founded a company to develop catalytic converters for cars technology that wouldn't become mandatory on American vehicles for another 2 decades. but that traces directly back to the same catalytic principles he'd spent his life perfecting. The fixed-bed Howdrey units themselves were eventually superseded by more efficient fluid catalytic cracking systems, refined further by other engineers in the years after the war. But the fundamental idea Howdrey proved at Marcus Hook in 1937, that a catalyst, not just brute heat, could crack crude oil into far more, far better fuel, never stopped being the backbone of the industry. The same basic principle he defended against a decade of expert dismissal is still, today, how the majority of the world's gasoline gets made. Howdrey received honors for it eventually, honorary doctorates, industry medals, a posthumous place in the National Inventors Hall of Fame. But he was never a man chasing glory. He'd quit a comfortable family business to chase an idea nobody believed in, funded years of failure with his own money, and kept going through a depression that killed the project everyone else thought he should have abandoned. When the recognition came, it came late, and it came for the fuel, not for the man who nearly gave up his fortune to make it real. There's a version of this story where the largest oil companies in the world get credit for winning the Battle of Britain's fuel war. That's not what happened. It was a mechanical engineer with no chemistry degree, testing crushed clay in a Bugatti, who they told for 13 years was wasting his time. The lesson isn't really about fuel. It's about who gets to decide what's impossible and how often they're wrong.